Welcome to Salt and Siren, the current situation. I'm your host, Brianna, a marine biology student, a mother, a military wife, and a lifelong lover of the ocean. And in this podcast, we are going to take a closer look at what's happening beneath the surface. So let's dive in. Welcome back to Salt and Siren, the current situation. In the last episode, we briefly discussed interconnectedness and why caring comes before conservation. Today, we're going deeper into the current to talk about some not so pretty stuff. Let's dive in. Did you know coral reefs make up less than 1% of the ocean floor, yet they support nearly a quarter of all marine life? That number alone should stop us for a second. An ecosystem so physically small, barely visible on a map, somehow carrying the weight of entire food webs, coastlines, fisheries, and cultures. It's not just impressive, it's structural. Reefs aren't just beautiful places where colorful fish live. They're protective barriers. They're nurseries, they're foundations. They're built by tiny coral polyps, animals smaller than your fingernail, powered by microscopic algae living inside their tissues, and stabilized by an invisible network of relationships that stretch far beyond the reef itself. So when coral declines, the damage doesn't stay contained. The effects ripple outward through food webs, coastal systems, and habitats that may not look connected at first glance. Fish populations shift. Predators lose hunting grounds. Juvenile fish lose nurseries. Sediment begins to move differently. Water chemistry changes. And sometimes you can see all of that change reflected in the behavior of a single animal. Today, that animal is the green sea turtle. Not a symbol, not a mascot, but as a lens. Because this episode isn't just about coral loss. It's about how ecosystems respond and what recovery actually looks like when it happens. Coral decline isn't a future possibility anymore. It's measurable, it's documented. Scientists don't argue about whether it's happening, they argue about how fast, how unevenly, and how much time we have left to slow it down. Over the past 30 years, we've lost roughly half of the world's coral reefs. In some regions, parts of the Caribbean, Southeast Asia, the losses are even more severe. The primary driver is temperature. When ocean waters stay just 1 or 2 degrees warmer than normal for too long, the algae living inside coral, their main energy source, are expelled. The coral turns white. This is bleaching. If conditions stabilize quickly, corals can recover. If they don't, the coral starves. But reefs don't collapse all at once. They fade. Color drains, life thins, the underwater soundscape quiets. And that silence is measurable. Healthy reefs are surprisingly loud. Crackles from snapping shrimp, pops from fish communication, a constant biological chatter that tells larvae, fish, and invertebrates this place is alive. Damaged reefs grow quiet. Recovering reefs begin to hum again. And yet, even in that quiet, there are signs of resistance. Coral fragments regrow. Restoration teams replant nursery-raised corals. Some colonies survive heat waves that should have ended them. Genetic lineages that tolerate higher temperatures better than others. The ocean is not passive. It is constantly adjusting, recalibrating, searching for balance. And this is where our story really begins. When coral declines, the balance of the coastal system shifts. Herbivorous fish populations change. Algae grows unchecked. Sediment increases. Light penetration decreases, and the seagrass meadows, sometimes miles away, the effects begin to appear. This is where the green sea turtle becomes more than a charismatic species. It becomes an indicator. Green sea turtles are what ecologists call ecosystem engineers. Their grazing patterns shape the structure, productivity, and resilience of seagrass beds. Healthy seagrass grows short, dense, and nutrient rich. Overgrown seagrass becomes tall, weak, and prone to disease. Turtles keep it trimmed, oxygenated, alive. But when coral declines, that system begins to strain. Sediment clouds the water, algae competes with seagrass, light becomes scarce, so scientists watch the turtles. Not because turtles cause the problem, but because their behavior reveals it. A turtle traveling further to find food is telling us something. A turtle shifting its grazing grounds is telling us something. A turtle abandoning a meadow entirely is telling us something. And sometimes, a turtle returning after years of absence is telling us something too. Recovery leaves a signature just as clear as decline. There's a shallow, protected bay in the Pacific where researchers have monitored green sea turtles for decades. At first, the changes were subtle. Seagrass thinned slightly, grazing paths widened, turtles spent more time searching. Then, coral offshore declined further. Sediment increased, water clarity dropped. Some turtles left the bay entirely. Years later, conservation measures began to take hold. Coastal runoff was reduced, water quality improved, coral cover offshore increased, not dramatically, but enough. And slowly, blade by blade, the seagrass returned. The turtles followed. Not all at once, not in a dramatic surge, but steadily, predictably, as if responding to an invitation. This is the part of marine science that feels almost like storytelling, not because we're projecting emotion onto animals, but because ecosystems behave with a kind of narrative logic. When conditions improve, species respond. When habitats recover, life returns. The ocean is always trying to stabilize itself. If you follow a green sea turtle long enough, you start to see the ecosystem through its decisions. Researchers attach small satellite transmitters to turtles. Lightweight, hydrodynamic, designed not to interfere with natural behavior. These tags record location, dive depth, and movement over time. The data doesn't just tell us where turtles go, it tells us why. After bleaching events, turtles often increase travel distance. Their foraging ranges expand, their movement patterns become less efficient, grazing paths that were once tight and predictable grow scattered and irregular. This isn't anecdotal, it's statistical. Scientists overlay turtle movement maps with temperature anomalies, sediment load, light penetration, and seagrass productivity. The turtle becomes a moving sensor, a biological instrument tracking ecosystem health in real time. And when recovery begins, the data shifts again. Travel distances shorten, grazing loops tighten, movement becomes efficient. Long before it looks healthy to the human eye, the turtle already knows. Part of what makes green sea turtles so effective in this role is their physiology. They're the only primarily herbivorous sea turtle species. Their jaws are serrated, built for cropping through plant material. Their digestive systems are unusually long, allowing time for microbial fermentation. Inside their gut, bacteria breaks down cellulose much the same way it happens in grazing mammals. That matters because turtles don't just consume seagrass, they process it. Their digestion releases nutrients back into the environment in forms seagrass can immediately use. This creates localized nutrient cycling loops, effectively fertilizing the very meadows they depend on. It's a closed feedback system. Grazing stimulates growth, Digestion recycles nutrients. Nutrients fuel regrowth. Regrowth stabilizes sediment. Remove the turtle and the loop weakens. Return the turtle and the loop repairs itself. This matters for another reason we don't talk about nearly enough: carbon. Seagrass meadows are one of the most efficient natural carbon sinks on Earth. Pound for pound, they store carbon faster than tropical rainforests, and they store it differently. Carbon captured by seagrass doesn't just sit in leaves. It's buried into sediments, locked away beneath the meadow, sometimes for centuries or even millennia. Scientists call this blue carbon. But blue carbon storage depends on structure. Healthy, grazed seagrass grows quickly and pushes carbon downward into sediments. Overgrown seagrass collapses, becomes prone to disease, and releases stored carbon back into the system. This is where turtles return to the story, not symbolically, but chemically. Green sea turtles maintain seagrass in its most productive state. Their grazing increases carbon uptake, stabilizes sediment, and helps lock carbon away long term. So turtle recovery isn't just about turtles, it's about climate regulation. It's about sediment chemistry, it's about carbon storage on geological timescales, and it's measurable. At first glance, coral reefs and seagrass meadows look like separate habitats. Different depths, different species, different structures. But physically, they're coupled. Reefs act as wave barriers. They reduce energy before it reaches the coast. When reefs erode or flatten, wave energy increases. Sediment is resuspended, light penetration drops. Seagrass needs light. Even small reductions in clarity can push a meadow past a tipping point. So a bleaching event offshore can starve seagrass without touching it directly. The turtle feels that change before we do. The turtle story, though, isn't just ecological. It's historical. Green sea turtles have existed for more than 100 million years. They survived mass extinctions, they survived ice ages, and yet, in the last century, their populations collapsed, not because of natural cycles, but because of us. Overharvesting, bycatch, habitat loss, pollution. Many populations were pushed to the brink. But here's the part that matters. When protections were put in place, turtles responded. International trade bans, protected nesting beaches, fishing gear modifications, long-term monitoring. Because of sustained conservation efforts, green sea turtles are no longer classified as endangered globally. Some populations have increased by nearly 30% since the 1970s. Certain nesting beaches now host tens of thousands of females each season. This didn't happen quickly, it didn't happen easily, and it didn't happen everywhere at once. But it happened, and that matters. Recovery doesn't mean the story is over. Climate change introduces new pressures. Rising sand temperatures skew hatchling sex ratios. Sea level rise floods nesting beaches. Stronger storms erode reproductive habitat. Recovery is not permanent. It's conditional. Which is why green sea turtles aren't a fairy tale ending. They're a living experiment in what sustained protection can accomplish. Healthy reefs are loud. That sound isn't background noise, it's information. Larval fish use sound to locate habitats. Crustaceans synchronize behavior based on acoustic cues. Entire communities orient themselves using reef noise. When reefs fall silent, recruitment slows. When sound returns, life follows. This is why soundscape restoration works, not because it's gimmicky, but because it restores a missing sensory signal. Scientists studying reef soundscapes have found that healthy reefs are loud, not in a chaotic way, but in a patterned biological way. Snapping shrimp crackle constantly. Fish communicate with pops and grunts. Larval organisms actually use these sounds as cues, helping them decide where to settle. A damaged reef grows silent. A recovering reef begins to hum again. Because marine life responds to these acoustic signals, researchers have experimented with playing recordings of healthy reefs at degraded sites. The results are promising. Fish return more quickly, bringing nutrients and movement that help kickstart recovery. Which leads me to a thought that is, scientifically speaking, not entirely unserious. Okay, so we have Taylor Swift, the Eras Tour, the last show, the end of an era documentary. So it feels reasonable to suggest that an Eras Tour Under the Sea edition could be excellent for reef restoration. Imagine a track that blends reef crackles with Taylor's vocals, not because fish are Swifties, although, honestly, who's to say, but because the soundscape would signal that the habitat is alive again. Now, I'm not saying All Too Well, Taylor's version, 10-minute version, could completely restore a reef. I'm just saying the emotional arc helps. If we step back far enough, a pattern emerges. Not perfection, not inevitability, but response. The ocean responds to relief. It responds to protection. It responds to time. Green sea turtles are living proof of that response. Which brings us to the question this episode leaves hanging. If we can change the trajectory of a species that migrates across entire oceans, if we can repair feedback loops that operate on geological timescales, if we can measure recovery in movement, sound, and chemistry, then who else is still waiting? And why haven't we tried hard enough yet? Coral reefs, seagrass meadows, and green sea turtles are not separate stories. They are chapters in the same narrative. One thread pulled, the tapestry shifts. One thread repaired, the tapestry strengthens. Next time, we'll follow that thread into deeper water. Episode 4 is all about sharks, not the villains we were taught to fear, but the stabilizers ecosystems depend on. For now, we end here, with coral, with seagrass, with the turtle grazing in the shallows, and the reminder that recovery isn't hypothetical. It's already underway. Are you ready for it? And that's all the tide brought in today. I'll meet you next time where we'll keep exploring what lies beneath the surface.